Good evening, everyone. Welcome to join our week 7 review of business analytics. I hope you have had a great week. This week, we built on what we learned last time so that we practice probability in decision-making. Any questions so far about the concepts we learned on decision-making and also the homework of week 7?
Hey, Jerry, it's T. I did have a question. Hi,
Okay.
how are you doing?
Fine.
All right, good.
Still alive.
Yeah, still safe from all the rain. So I did have a question for the homework. I don't know if it would be appropriate to ask now or save it for later.
Well, how about now? Yeah.
Okay, sure. So it's for the decision tree. So I have it in my notes. For the decision tree, when we get to a decision, we choose the best alternative. And then when it's a chance, we calculate the expected value. So when I made my tree, there's a chance regarding the patent versus no patent. So patent 70%, no patent 30%. I wasn't sure how to calculate that chance, or is that already, it just is, and there's nothing to calculate?
Oh, okay. The 70% given is the chance. It's the probability.
Right. So it's given, there's nothing to calculate versus like the values at the end where whether it's high, medium, or low demand. I know there's a calculation between the expected revenue if it's high and the chances of it being high demand. So for the patent, no patent, it's just given.
I mean, what's given is the probability, but we can still calculate the expected return or the profit based on these given probability.
Right, but that's what I'm saying. So what I'm saying is for the chance of it being high, medium, low, because we're given a probability of it being high versus medium versus low and a dollar amount, in that case, for that chance node, we can calculate for each one. But for the patent versus no patent, there's nothing to calculate. It's just 70% and 30% because it's given. Does that make sense?
Yeah, although I think there's still something we need to calculate given the chance of getting a patent. Let me illustrate what I mean. So let's walk through problem 2 together first. Let me know whether you have questions regarding other problems. Let me share my screen so we work on problem 2 together. So here, week 7, we have the decision tree making. So first, we need to recognize that in this problem, we need to make a decision eventually about whether to pursue continuing the development or not. This is totally dependent on the expected profit out of the project. And to calculate the profit, we need to remember a very simple equation. Profit equals the difference between revenue and cost. When we take expectation, when I mention expected profit, which depends on whether we continue the project or not, it's simply the expected revenue minus the expected cost. And if we must condition this expectation on some other event, this event could be any decision we make throughout the decision tree. For example, whether the patent was awarded, whether we did licensing or the development and manufacturing or marketing. Then we simply take the conditional expectation. So usually we were given the tree from the root to leaves. However, to get the expected value of the most to get the expected profit from the first decision, we need to work from we need to work backward from downstream to upstream. So let's first walk through each step so we understand how many steps and what decisions are involved. And for T, the question was on this. There's a patent step involved, and she was not sure whether we need to calculate anything in this step. So let's see whether it's necessary. First, we know that the first decision is about whether to continue the development at all. So we have, let's see, steps. So first is to continue or not, right? So if we continue, then that's goes to second step. If continue, then we have cost, which is 2. Then there's a patent involved. 70% getting the patent or 30% not getting the patent. Then if the patent is awarded, then there's another decision making. So there's a third step that's about patent. So we have 70 versus 30% of chance getting it or not. And in fourth step, we have licensing or getting the development and the marketing. So if we get licensing, we have a 25 million royalty. However, if we sell in-house, there's a cost, but there's also expected value depending on the demand. The demand comes in 3 levels, as mentioned by T, and at different probability, and also associated with each of them is the expected revenue. So that means after this step of patent, so fourth, if patent, then we have 2 decisions: licensing or development and marketing. And also there's another step that involves details in development and marketing. We have already learned and practiced this last time. Remember that in probability, we have calculated expectation. Last time it was about expectation of investing high and low, right? And in that case, I mentioned that expectation is nothing but a weighted average. We weight the value of different scenarios by the probability of the scenario. This is how we calculate expectation for a discrete random variable. This is exactly how we calculate expectation, for example, for a coin flipping or throwing a dice. Nothing more complex than that. So in this case, we can easily work from the bottom level. So at DMM, we have 3 probabilities and 3 revenue, right? However, remember, we also have a cost associated with it. So when we calculate the profit, it's a weighted average. We would take the product of 0.25 and 55. That's the revenue. If the demand is high, we take expectation. Then we plus the product of these 2. Then plus the product of these 2. So we have 3 scenarios, and we weight the expected revenue with the probability of 3 scenarios. However, remember, we need to also remove or deduct the cost if we pursue development in-house. So in that case, this is what I got when we calculate the expected revenue, expected profit if we do development marketing. I also removed the $2 million cost of continuing the project. This is obvious because if we already go into the decision that we do the development and the marketing step, then it necessarily means we continued the project, and it would mean that there's another $2 million because we chose this branch. Any question here? Great. Now we know that if we chose development and marketing, the expected profit, the difference between revenue and all associated cost would be 22.9 million. So if we do licensing instead, know that what's given is the revenue of licensing. So if we already have the license, so here we don't have to take care of any probability of getting patent or not. So we already know we chose licensing, then the expected profit would be 25. That's the revenue of licensing, right? Minus 2, because that means if we got the license, that means we already continued the project. So we remove the $2 million cost of continuing the project. That's how I derived the 23 of expected profit if we pursue licensing, if we got into the step of licensing. So these two are the most downstream decision. So between these two, we need to make a choice. Which of these two are higher? Obviously, it appears licensing gets a slightly higher profit. That's why between development, marketing, and licensing, we would choose licensing since it gives us a larger expected profit. That completes the step, the most downstream decision making. So if we already moved to the stage of whether we should choose between development and marketing or licensing, we would choose licensing. All right. So now it comes to the step where a student got a question. So about the patent awarded or not. We also have a probability associated with it. But to see it clearly, we must go into each scenario. If we already know the patent was awarded, then it would allow us to move downstream, right? It would allow us to either choose licensing or development and marketing as the further step. So at this stage, if we already know we have the patent awarded, we will definitely do the licensing step and got 23. That's why the expected profit of patent awarded under that scenario is 23. There's no difference. We don't have to calculate further in this part. But if the patent was not awarded, then it means at this stage, we already paid the continuing cost of the project, which is 2 million. So that's why the expected profit would be negative 2 million. All right. Now, if we combine these two scenarios, that's where we need to take care of the chances of getting awarded or not. So this comes at the stage that's beneath continuing the project. So if we already know we chose to continue the project, then that's where the chances of awarding patent comes in play. Here, to calculate the expected profit of continuing the project, we do need to take the expected value of profit under both scenarios of a patent awarded or not. That's why I take the weighted average. So if the chances of getting 23, which is when the patent was awarded, is 70%, the chances that we get -2, which is the expected profit or the loss, if the patent was not awarded, was 30%. So that means we would have to combine these two pieces of information. So 70% times 23, right? And there's a 30% chance that we need we would have a negative profit. So that would be the expected profit if we continue the project. And of course, if we do not continue the project at all, then the profit would be 0. Nothing would change. That's how I derive the expected profit under each step. Any questions?
That was really helpful. Thanks, Jerry.
Oh, wonderful. So through this process, as you can see, what we did is simply to work from downstream to upstream. We derive the expectation, either in this case, it will be profit. And to calculate profit, we have to take both revenue and cost into consideration. The cost that happens upstream would be carried down in any downstream decisions, right? And if there were any profit already happened in upstream, we would also carry it down. But in this case, all the profit happened in most downstream stages. So that's why we do not see that revenue passes through. So we would choose whatever upstream decision that gets higher expectation if there's no chances coming with it. So for example, the most downstream decision between development, marketing, and licensing, we do not take an average of these two scenarios, but choose whichever gives the higher profit. Great. Any questions regarding decision tree making? All right. How about other questions and problems? In problem 2, we also need to play with expectation. And in problem 3, it's a simulation. Did you have any questions in any of these two parts?
Jerry, I joined a few minutes late. I have a question on problem 1. I think I'm stuck in the last part of the question.
Okay, the last part is about expected value of information. How did you plan to address this question, though, if you have any ideas?
It wants to maximize expected value. What is the maximum amount they should be willing to spend? So I thought whatever is the lowest investment level, right, with expected value, that should be what they should spend.
Oh, okay. I'm not sure what lowest you meant.
For example, like I calculated the expected value.
Okay.
For low investment and high investment.
Oh, okay. Excellent.
And whatever value I got for the low investment, I thought they can at least spend that much.
Oh, I see. No, unfortunately, that would be an incorrect approach.
Okay.
So how about we take a look at them together? So let's see. Let me move forward. Upward. So in the first question, we were given this payoff table, and everything was derived from it. In problem 1 part D, the last part is about expected value of perfect information. And to work on that, we also must to calculate some expected value. It seems you already did an excellent job in calculating expected payoff under both scenarios. For example, you mentioned that you calculated under if we invested low, then expected payoff is of course the weighted average and of the row-wise weighted average, right? If this is low, then we just use the given probability as the weights and to weight these 3 payoffs. enter this on this row. And we do the same thing for high. This is exactly how I calculated the expectation. And to complete part 3, we would simply compare these two expectations to choose whichever gives us a higher expected payoff. So we did that very well. Given that, we would work on problem part D about expected value of information. So before that, just take a small break and consider what it means by the value of information. The question here asks us that the purpose of the department is to maximize expected value, right? Then there's also maximum amount of willingness to pay for information about the market share. So this means that given the market share information, we would have a better decision making that leads us to a better payoff, expected payoff. Then only when this expected payoff with the market share information is higher than that without the market information, then that's where the value of information shows up. If there's no, if given any market share, we don't earn more, then there's no value of the market share information. So here, I think what's critical for the correct approach is that we have to choose the correct anchor point. So this anchor point is not the lowest expected payoff. It's actually the higher between these two. So at this stage, when we calculated the expected value of payoff, if we chose low or high, we do not have any further information about the market share, correct? So without buying the information, we already made the higher payoff. Then let's see if we could make a better decision if we get any further information regarding market share. This information comes in the form that, let's say, consulting firms give you a report saying that we are very confident market share will be either low, medium, or high. Either it's smaller than 1 or between 1 or 4 or larger than 4%. It can be either of these 3, right? But remember that when we buy this information packet from the consultant, we don't know the content. You must pay this cost before opening the packet, right? So it's like an empty, like a blind box.
Yeah.
So before that, what we know is that this piece of information comes at, the content comes at some probability. Because we need to estimate the value of this information packet before we read it. Otherwise, if you already read it, then you don't have to pay extra for the consultant. That's totally the essence of doing consulting. Don't share too much of what's already in your product. So this piece of information comes in this way that we have to fill this blank. And the chance that the packet has the information saying that the market share is smaller than 1% is 30%. So we have these probabilities, but we don't know exactly what's inside of the information packet. All right. So now, if we have the perfect information, it means if once we get the information packet, if it says that it's smaller than 1%, what would we do? We would definitely choose the better, we would definitely choose between low and high that gives us the better payoff. And according to this table, that's given. And if the market share is smaller than 1%, we would definitely choose low. And according to the same principle, if the information packet tells us that market share is between 1 and 4, we would also choose low. But here, the next step is different. If the market share says it's larger than 4%,
Yeah.
then we would choose high. That's why this decision making is different than without getting the information, right? For example, when we take expected value of payoff without knowing further information about the market share, then every piece of these expected payoff is coming from low if we calculate the payoff of a low expectation. Instead, every piece of payoff would be associated with high if we are calculating the expected payoff of high. But with the perfect information, this would change. If the information package says the market share is smaller than 1%, then we would choose low. We do the same under medium market share, but information packet, if it says that it's larger than 4%, we would instead choose high. So this is where you see it's different. When calculating perfect information, when we calculate the expected payoff given perfect information, that's how we do it. So we have another version of weighted average, but note that compared to the above situation without information, what's being weighted is different. The weights are still the same because we don't know exactly what's inside of the sealed information packet. So we assign some probability of some previous knowledge about which of these 3 pieces of information content would come to us. So with this, another version of payoff, expected payoff, but it's under the condition that we have the perfect information calculated, then we compare these two.
So with the perfect information provided to us, we already got the payoff, right? Of the expected values. Is that not perfect information? You're saying we got the probability and we got the investment type, high or low, and we got the market share already. So that was perfect information, right?
Yeah, but do consider that we would have to estimate the value of the information or pay for the information before we know what's inside the information.
Okay.
That's why, although it's called perfect information, at the moment when we buy at the moment before we buy, or at the moment we would need to pay for this piece of information, we do not know exactly what's the information is. So that's why we still need to use the probability.
Got it.
All right, then so we simply compare these two scenarios without perfect information. We would choose between the two investment levels that yields higher expected payoff, right? So this step is exactly mirrors what's in part C already. So we compare these, 2 or 3 expected payoffs. So in part C, we already know that we would choose either low or high, depending on which gives us a higher expected payoff. And then we carry it downward in part D also and compare the conclusion in part C with this calculation in part D. Then we would take the difference. So we know that this expected value of information is simply the expected payoff given the information and the expected payoff without the information.
Okay.
Excellent. Any questions about part one? I mean, problem one?
Jerry, could you for D, could you clarify one more time how we solve that?
So you're saying, Jerry, sorry, T. So you're saying that whatever we get as the higher payoff for C is what we will have for E also.
No. No.
Very good.
Well, what I mentioned is that the calculation done in part C, when we calculate expected payoff, comes in play in some parts in part D as well. So we don't have to recalculate everything.
Okay.
Yeah. So I recall that another student would want me to walk through it again. So how about Rachana, that you do the process? I could also assess whether you understood what I just discussed. Then I can also make some supplement and elaborate on any part that you do not have clear yet.
Okay, I'm gonna try my best.
So
in part
now
C,
you are to answer part D again.
yeah.
Or,
So in part C, T, we did the calculation where we individually took the low and the high and did the estimated or expected value of payoffs. But when you look at part D, I think we don't have any information on the market share or what is high, what is low, etc. So that kind of data is missing. So just by looking at the numbers, we are calculating the expected value of payoff, and then we're going to do a difference between them to see how much, or not a difference. I think we're going to pick the one which is higher.
okay. So could
amount.
you pause there? So
Yeah.
first, to address D, we need to understand the most important to understand the essence of the approach is that value of information is simply the difference of payoff with the information and without the information, right? If with this extra piece of information we have extra payoff, then this additional premium would be the value of information. That's simply what's written here. That's the logic that we walk through. And given that, because of this, we would have to calculate each piece of them. And as Rachana mentioned, we have already calculated the expected value of payoff under the no perfect information scenario. That's exactly what happens in part C. Now we need to calculate this extra piece of information. That's the expected payoff given perfect information. So could you walk more to elaborate on how we calculate this piece of information highlighted in my shared screen, Rachana?
So you will have to take the probability, and you'll have to use the information of the payoff at that probability for each of the values and then sum it up.
Okay, excellent. That's exactly what's written here. And as I illustrated earlier, what's very important is that getting the right payoff under each scenario. This perfect information could say that it's the market share is either smaller than 1, between 1 and 4, or larger than 4. I illustrated 2 parts. You can easily fill out the middle scenario. Then we do need to find the correct payoff under each scenario. I walked through this in the discussion that if the information says that market share is the smallest, that's smaller than 1%, we would definitely choose low. Because of this extra piece of information, we would choose low. We don't take an average between low or high, right? Do the same for the medium market share scenario, if this extra piece of information tells us that market share is 1 to 4%, we would also choose low, because in that scenario, low investment also gives us a higher payoff than that of high investment. But if the market share information tells us that it's larger than 4%, we would definitely choose high, so that we get the higher payoff in this scenario. Then we weight every of these 3 scenarios. Then we get an expected value of payoff given that we have the market information.
Okay, I think I'll tell you where my confusion was coming from.
Okay.
For part C, I actually did what you did for part D. I looked at which of these investment levels and market share would give me the higher payoff, and I just summed them up.
No, you cannot do it because if you sum expected value, these two, if you sum these two, then no, it doesn't make sense.
Mm-hmm. Got it.
Don't do that.
So so the EVPI is just the difference between those two, and that's sort of the value of that. The information is the difference between having the perfect information and not having it. Is basically the value or the premium you're placing on the information to.
Yeah, exactly. Great understanding.
And would there ever be a situation where there's partial information, or would it either be perfect or not perfect?
Oh, I see. Well, you don't have to overcomplicate the situation. In our question, this is exactly what we need to practice. If what you mentioned might be more more complex than what the question requires.
Okay.
All right. Any need for clarification? All right. I also provided some guidance on how you can work out part A and B on optimistic decision making and regret minimization. It should be quite helpful. Do we need to move on to the simulation case? Any questions on that?
So we're just simulating the costs and the revenues based upon the trial, the random values, and the information given, and then using that random value to look at the maximum and minimum based upon each trial.
Yes, exactly. That's the charm of doing simulation. It simplifies all the scenario. I mean, it simplifies the process. So we have some tangible samples to use. Okay. If you don't have particular question, how about I walk through my notes, because I added a few more pieces of information that really helps you understand what we are doing. So any questions?
No, Jerry, we can walk through.
Okay, all right. So in problem 3, we are given this table, and we know that the random A and random B column are generated by the random number generator function. So before doing that, we need to understand what we are doing. So the purpose of this is to simulate the profit, so we understand the distribution of the profit. Then, for example, in part A, right? Yeah, we are calculating the minimum, maximum, and average profit. This is very relevant. If you are the manager of a factory, you want to make some prediction of the next month production. Then if your stakeholders are asking, oh, what's the probability of us getting a profit larger than this threshold? To calculate this probability, it's somewhat difficult if this sample is not available, right? It's in the future. You need to make prediction. And this distribution of profit could not be easily mimicked by some known distribution. So that's why we use simulation. And to achieve that, we calculate profit based on cost and revenue. And the revenue depends on demand, right? So what we are given are the distribution about cost and demand. And we use that to build up cost and revenue, then use the very simple relationship to calculate profit out of that. So if we know the distribution of cost and demand, we could easily simulate some observed values of cost and demand as a simulated sample, and use this sample to calculate whatever function out of it. And in this case, the function is simply revenue minus cost, which gives us profit. Any questions in the principle of this problem? All right, understanding what we are given and what we need to do, then the next step is to understand how we need to realize a simulation case. And I encourage you to read first the process of addressing probability questions in week 7, right? Yeah. Ooh. In week 6 notes. In this week 6 notes associated with calculating all the conditional and the joint probability, I provided you with the process of how to address probability questions. Particularly important is that first we need to understand what variable we are calculating the probability for. Defining the variable differently would lead us to different approaches to the same question. Then we organize known information, what we know about the distribution and statistics. Then we calculate further things. It also carries on in our week 7 simulation case. For example, first, we need to organize known information. Here in our case, we're given 2 random variables, right? First is cost. Second is demand. And we know that each of them is continuous. And we also know the distribution of each of them. Note that it mentions clearly saying that first, cost per month is anywhere between these 2 values with equal likelihood. It means that we are seeing a uniform distribution. This uniform distribution means that any value between the minimum and maximum has equal likelihood. And that's exactly what it means. So we know it's uniformly distributed. We also know about the distribution of demand. It's normally distributed with mean and the standard deviation. So we know these information about distribution already. And for the distribution parameter of a normal distribution, we also know the mean and standard deviation. Okay, next step is already given, but normally that's where we need to generate random variables using a random number generator. This gives us a uniformly distributed value between 0 and 1. So what we're doing in this step is actually generating cumulative probabilities. Remember that any probability is a value, a fraction between 0 and 1. And because this random number generator gives exactly a random number between 0 and 1, so that's why we use this random number generator to yield all these cumulative probabilities. And in our case, to guarantee this reproducibility, we are already given these random numbers. But let's see how you could actually do it yourself. In other cases where you're not given a version of random number, then you can simply use this random number generator. See that I use exactly the same function to generate them. Notice that whenever you make any change to the sheet, this random number, these random numbers are will be regenerated. For example, if I type, see that these two columns changed. If I remove, see that these two columns changed again. So it's very important to understand that whenever you use a random number generator function, this rand with parentheses, it recalculates each time you open the file or you change anything onto the sheet. So that's why if you want to maintain the reproducibility, so the next person, whoever re-examine your work, wants to get exactly the same outcome, you would have to keep these things, lock these cells, or copy and paste so that it doesn't change again if you do any alteration on the sheet. Okay, so that's where we have the cumulative probability. But why do we have these probability? Since what we calculate is it's nothing about probability, right? But you will understand once we go one step ahead. The reason is using the probability, it easily gives us observed values. So this is exactly what this next step is doing. And this is exactly what we need to do onto the sheet that we are given. Let me illustrate what it means. Here we need to transform cumulative probabilities, that's exactly the random number we were given, to corresponding quantiles using quantile function. But otherwise, it's also known as inverse cumulative distribution function, which is exactly the function called in Excel inverse normal distribution function, right? Of a specific distribution that X follows. X here, in our case, would be cost and demand. So in this step, we are transforming P to X, given that we know this very apparent function about cumulative probability. So that we can get X based on P. And that's exactly what some inverse cumulative distribution function does. Okay, that means given column random A and random B as values between 0 and 1 to represent cumulative probabilities, we are going to transform them into the observed values that we actually care about. That's cost and demand. How did I do it? The cost, remember, it follows uniform distribution, right? So we simply time the minimum and plus the this product between this cumulative probability and the range. That's the difference between maximum and minimum value in the uniform distribution. So we are transforming a 0 and 1 probability to a 150,000 and 200,000 cost. So it's like a linear transformation. To transform a probability to a observed normally distributed random variable quantile, we would use this normal inverse normal distribution function. If you want to understand what it does, simply click this function name once it pops up, then it tells you that it returns the inverse of normal cumulative distribution for the specified mean and the standard deviation. So it transforms probability to quantile. So for example, if we know that a normal distributed random variable gets to a cumulative probability at 75%, it means it achieves at this particular value, that's 5,600. That's where this random variable beneath this value would cumulatively sum up to 75% of cumulative probability. So that's what it means. Then we have a column of demand. Notice that this average as shows here. Oh, okay. I also calculated in the cell. It's 5,350. It's pretty close to the given information saying that the population has a mean of 5,000. This is also a checkpoint to guarantee that to see how our simulation is. If it's too far away from 5,000, then it's probably because we made some mistake. But since in my case, based on the random number, and when I calculated the demand, this mean is close to 5,000, and the standard deviation is close to 1,000. I consider that it's not too bad a simulation. That's how we can check the correctness of simulated observations. Another way we could check the correctness, just in case we made any mistakes, is that we could observe each of the value to be that a larger p corresponds to a larger x. Remember, we generated x based on cumulative probability, right? So we also know that the cumulative probability is increasing with x. So we should always see that x increases with while p increases. And let's go back to our case. For example, comparing these two cases, when we move from trial 2 to trial 3, we see that p, the cumulative probability, increases. The same happened to cost, because cost was generated based on p, right? So when this cumulative probability increases, we also see that cost increases. And does it apply the same for demand? Let's see. Compare trial 1 and 2. When random b, that's the cumulative probability, increases, we also see that demand increases. It means that, okay, the function I use to calculate demand should work, at least not incorrectly. Any questions here? Okay, so this is some two ways of checking point to see, to spot any mistakes. And the last step is that we use the simulated sample to calculate whatever quantities we need. So once we generated cost and demand using the random number, we could easily generate revenue. Revenue is nothing but demand times 95. That's the price of each product. Okay, so we do the same for profit. Profit is nothing but the difference between revenue and cost. So that's exactly how I calculate each of these columns. And I also generated mean and standard deviation of each of them. What's required in part C, part A of problem 3 is the minimum, maximum, and average of profit. You can easily calculate each of these 3 pieces of information given this column of simulated profit. Any questions about how I got it at the step?
Gary, just to be extra safe, so for the minimum, maximum, and average, we can just do a simple formula for that, right? It's pretty straightforward.
Yeah, since if we already understand how I derived these simulated profits, then you're good with it.
Perfect. Thanks.
Okay. Now, I wonder how you addressed part B, how you consider how good the simulation is. Major flaws, actually. Okay. Any thoughts? What major flaws did you suspect?
Is it something like the independence between costs and revenues? Like there may be some kind of overlapping like values that kind of correlate like in the same way, like so it's not separated entirely.
Wonderful thought. So if we ever worked on profits, we understand that since we calculate profit is nothing but the difference between cost and revenue, right? So it's reasonable to consider that profit associated with both cost and revenue. So let's see what happens in our example about correlation and whether it shows a correlation as what we would expect in reality. So, for example, I calculate a series of correlation. What's the correlation associated with the random A when we have the cost value? So here I calculated the correlation between random A column and random B column, these two columns. And we see that the correlation is 1. Is this surprising? And if not, why do you think we have a correlation of exactly 1?
Because like the cost is directly derived from the random.
Yeah, very good answer. But this directly derived, it needs to be linear transformation. So if we ever linearly transform any variable, these two different variables would be perfectly correlated. Remember how we calculated the cost. It's nothing but a linear function of the random number, right? That's why they would, if we plot these two variables, they would exactly form the same on the same straight line. That's why we random number B column and demand these two columns. We see that we derived the demand based on random variable B, but it was not a linear transformation. We used instead the inverse demand inverse normal distribution function, which is not a linear function. That's why we see, although this correlation is very close to 1, but it's not exactly 1. However, when we calculate the correlation between demand and revenue, this again gives us exactly 1. As we just walked through, it's because revenue is nothing but the demand times 95. It's a linear transformation. So correlation would be perfect. Then here it comes again. If we calculate correlation between random number B and revenue, we would observe again 99%, well, 0.99. It's not a percentage. So this correlation coefficient is exactly the same as what we calculated as the correlation between random number B and demand. This is also expected because revenue is nothing but a linear transformation of demand, right? So if the correlation between random B column and demand is 0.99, then we would also expect the correlation between random B and revenue to be the same. That's 0.99. All right. What about the correlation between two series of random number? We see that the correlation between column A and random A and B were negative 0.37. So what are your thoughts about this? Is it reasonable? So my thinking is that since random A and random B represents the cumulative probability about the cost and demand, we should see that if we have higher cost, it means we produce more products, right? Then we should also do that when the demand is high. So we should somehow expect the cost and the demand to be positively correlated. Instead, in this case, the random cumulative probabilities are negatively correlated. However, this is not intended. It means that on average, we should expect this correlation to be 0 because of the way we generated the cumulative probabilities. See that every time when I have 2 columns of random numbers, this is the correlation between each of them. Let's see how it happens. If I change, so this correlation is very close to 0, right? But if we change again, well, it changes, but it's still pretty close to 0. However, sometimes we observe some positive or negative values of correlation, but all these happen randomly, so it represents nothing. Because the way we generate these 2 columns were exactly how I did it here. These 2 columns should be expected to be not correlated at all. However, this observed negative 0.37 as the correlation between these 2 columns just happened by chance. If we calculate the correlation between cost and demand, we see a negative 0.42. This also happened by chance. So on average, this particular way this particular method we do the simulation should give us a 0 correlation between them. However, this is not totally satisfying. We should expect, and in reality, there should be a positive correlation between cost and demand. That's what I consider, and that's also what the other student considered as a major flaw. That we did not factor in the natural correlation between cost and demand in this simulation. But there are ways that allow us to do so. It's called as a multivariate normal distribution. So we could, instead generating 2 columns of unrelated or independent variables, we could instead generate 2 columns of correlated random variables with some specified correlation between them. All right, so you could also check the correlation between random A and demand, which gives us exactly the same as the random A and a different one. So we could also check the correlation between cost and random B and all others. About the profit, let's see what happens here. If we check the correlation between profit and cost, they should be negatively correlated because profit involves a term of negative cost, right? So this correlation, when we calculate it, it's negative 5.4. The correlation between profit and revenue is positively correlated because in profit, revenue is a term and the coefficient is 1, right? So we expect them to be positively correlated, and the correlation was 0.99 in our sample. So we could check also the for the quality of simulation based on correlation of generated variables and examine whether it's reasonable or not. And as spotted by the other student, we should, instead of no correlation between these 2 random numbers, we build everything we build everything else based on these two. They should be correlated and also positively correlated. But instead, in our particular simulation, we assume them to be independent, although this particular round of simulation by chance shows that there's a negative correlation between them. Any questions? All right, with all this discussion, I think you should be all good with homework 3. Problem 3 in and also problem 1, 2 in homework 7. Any last minute questions? Otherwise, I wish you a wonderful weekend.
Thanks so much, Jerry. Have a good weekend. Stay safe, stay warm.
Yes.
Oh, okay. Thank you. Oh, well, one last piece of information that I almost forgot. In some previous homework and exam questions, I see that there are questions regarding probability. So to do that, given a simulation case, it will be simplified into counting the number of cells. For example, if I here as a investor of this company asking the manager of operation about what's the probability of getting a profit larger than 400,000, this question would be answered simply by the number of cells of the simulated profit to see which ones is greater than 400,000. I calculated as 4 of them to be larger than 400,000. So I would say out of 10 trials, 4 was larger than that. So I expect this probability to be 0.4 or 40%. Another similar question would be, what's the chance of the demand larger than 5,000? This is where some students would deviate in the question. The correct answer would be as simple as calculating the number of cells greater than 5,000. For example, I calculated 1, 2, 3, 4, 5, and 6 cells to be having a value greater than 5,000. I would answer 60% is the probability of demand greater than 5,000. However, some students overcomplicated this case by going back to the distribution. Because we are given that demand is normally distributed with a mean of 5,000, so we know that normal distribution is symmetric, right? So if from this distribution, we would know that the demand has half a chance of smaller than 5,000 and half a chance of greater than 5,000. So 50-50% chance. But this is not the process of doing simulation. If we already have a work example of simulation, we will simply do this proportion of cells approach. This is also mentioned in my notes. So that if we are calculating any probabilities, we simply use observed proportion of cell counts. So no need to ever overcomplicate the case. All right, that was the bonus piece of information. Have a great week.
Thanks, you too.
Thank you.
you.
Thank
Good
you.
night. Thank you.